A uniform conducting bar is in a magnetic field region as shown in the picture. The magnetic field is uniform and it points into the page. The bar carries a current of capital I in the direction from point A to B. We'd like to calculate the torque that the magnetic force applies on the bar. First, let's calculate the torque acting on an infinitesimal section of the bar that is shown as dx on the picture. So that torque, we will call that torque d tau. That will be the infinitesimal torque acting on that small piece of the bar. First, let's find an expression for the magnetic force acting on the infinitesimal section dx. Magnetic force is going to be equal to capital I, the current, times the cross product of vector dx times vector b. Now, vector dx is the vector pointing in the direction of the current, basically, and vector b is the magnetic field vector. So if we do a right hand rule on dx cross b, align your right hand in the direction of dx from point A to B, and then curl your fingers in the direction of B into the page. Your thumb points in the direction of the magnetic force perpendicular to the bar as shown on the picture. Now the torque acting on this segment about point A is x cross f sub b, x being the position vector pointing from point A to where fb is applied, and f sub b is the force vector as shown on the picture. Now that was the vector equation, and here's the magnitude of the torque acting on dx. It's x times fb times sine 90. Why sine 90? Because the angle between vector x and vector fb is 90 degrees. And by the right hand rule, the direction of this torque is counterclockwise. How do we determine that? Again, we're doing x cross fb. Align your right hand in the direction of vector x, curl your fingers in the direction of f sub b. So the curling of your fingers is counterclockwise. Also, you can think of the torque as a counterclockwise torque, or the direction of the torque vector is the direction of your thumb, which is out of the page. Similarly, the magnitude of f sub b is I times dx times b times sine 90, because the angle between the vector dx and vector b is also 90 degrees. And remember, sine 90, that's just equal to 1. So this is just 1. And this is also equal to 1. So in the next line, let's rewrite d tau with fb replaced with this expression. Here's what we get. The torque acting on segment dx is equal to I times b times x dx. Now let's calculate the total torque acting on the bar. Since we already have an expression for the infinitesimal torque, we will just integrate over this. So then total torque is equal to the integral of I times b times x over dx. In the next step, let's pull the constants outside of the integral sign. So we basically have some constant times the integral of x over dx. This is fairly straightforward. The integral of x over dx is x squared divided by 2, and x runs from 0 to capital L along the length of the bar. Evaluating our integral at the given limits, we get torque equals IBL squared divided by 2. Note that this result can be expressed as I times V times L multiplied by L over 2. I times V times L, that's the magnitude of the magnetic force acting on the entire bar. And L over 2 is half of the length of the bar. So this is equivalent to calculating the torque of the magnetic force IBL applied at the center of the bar.